is, that should be the right one. Okay. So I think I'm good to go. You're recording. We'll go ahead and get. So, is everybody done out in other places? Looks like a couple more people are coming in.
They're split. We've got a division B and a division C.
Well, this should only be C folks.
Yeah.
So,
Yeah. And the other event is only division B.
very good, very
So
good.
that's why they're running incorrect.
Got
You
it.
need people to be.
Nope.
Okay.
Negative. All right.
Okay, my sister teaches. Yeah.
Then whenever you guys are ready, we'll go ahead and start. Gabby said that the other group of people is all Div B, so they're not going to be joining us. So just a little bit of an introduction for, go back, make sure you're in the right place. So we're going to be doing the material science thing. The last time they did this was 2018 with polymers. So I, once again, have an event that they have not run in several years. And they have also changed what the target is so that I can't just go back to the last one and be like, oh, hey, this is what they did last time. So last time we did detectors and they totally changed what it was. And again, it was an adventure. So other than just some information about me, I have teach here at UT. I am the director of the advanced laboratories, and I'm also a lecturer. So I've got Gen Chem and analytical chemistry. And back in my previous job, I taught lots of different chemistries, including material science. So I am kind of a material science. I do the least amount of chemistry and still have it be chemistry. So lasers and maths, not beakers and flasks. But see, there are some nanomaterials. They're actually small gold and silver nanoparticles. For you guys, what's important is that I do Science Olympiad. I'm also the person who does the GSSE chemistry, and my focus for that has been nanotechnology. I also do one of the science fairs that I cannot remember the acronym for because they're all like 12 letters long. So you might see me again in some other capacity. So what is material science? We'll just go over a quick, brief bit of that. It's the study of properties and applications of materials of construction or manufacture, such as ceramics, metals, polymers, composites, and how they can be improved or created for real-world applications. So it's an interdisciplinary field that combines physics, chemistry, and engineering. It is the science of what I like to call stuff. So in Gen Chem, and then even up into analytical chemistry, we do a lot of stuff that is a liquid, right? And sometimes we do stuff that's a gas. And pretty much the only time you ever deal with the solid is I need to go measure some of this out on a balance and then go mix it with, and then I get it into a liquid. So we don't spend a lot of time doing stuff in the solid state as chemistry people on that introductory level. But that's really important because all of the stuff that is literally around you is stuff that is going to be materials. And so it's the chemistry of stuff, which is how I kind of got into that. But there's lots of things that go into that. So really what you're looking at is in the fundamental, they love this little tetrahedron here that has structure and properties and performance and processes and how those things all interact within a material. And then you got lots of other things that are surrounding that are important, like what elements are they made out of? What materials are they? Do they have process property profiles? How do you pick something? Which physical phases are they in? And how do you make these things? And so it's a really, really, really broad field because materials show up just about everywhere. There are lots and lots of resources out there for materials science. What I'm going to do is kind of focus in on what I have learned about this particular event and kind of take us through the rules and some of the things that I found that might help us out with the fact that this thing is going to work in 3 sections. So this says kind of a big event in that there is a test component, a written test. There is a experimental part where they're going to make something and then test a concrete hockey puck. And then there is a third part where we're going to have them do something in a lab. And the first two parts are pretty straightforward to understand. Here is a test about material science stuff. I will give them a test. They will answer test questions. There is their build component where they're going to make this hockey puck. We're going to test it and they're going to drop it and see if it breaks. Also fairly straightforward on that, but we'll go through some of the rules. And then there is that third component, which has been a little bit mysterious to me because there is not that much information out there, but I have found some stuff that I'm glad to share with you. So let's look at the event parameters because we're going to start off with what do you need to do? So everybody needs to bring goggles, a lab coat or apron, a writing implement, which I did not bring. You can bring a standalone calculator of any class up to type 2. Now, in this PPE, you also have to include a 90th. Thank you, brain, N95 mask. So we'll talk about that in a second too. Each participant may bring one unique 8.5 by 11 sheet of paper, which may be in a sheet protector or sealed or laminated with information on both sides in any form from any source. So they get themselves a cheat sheet. I don't care. They do not care what goes on that cheat sheet. It can be on both sides. You can laminate it if you want. 50-50, we're not going to get that wet, but I also know what I was like when I was that age, and if I made that thing up even the day before, it would have been wrinkled, stained, and destroyed by the time I got to the actual competition, so it might be worthwhile laminating it just because I've been there and I know what that's like. All right, you can bring any oral items listed on the Div C Chemistry Events Lab list. Teams not bringing these items probably really won't be at a disadvantage. We were not going to provide everything that is on that list, but I would try to see too that for that lab component that they would pretty much have all the stuff they would need other than their PPE. Participants must wear goggles, an apron or lab coat, and have skin covered from the neck down to the wrist and toes. Closed-toed shoes. I spend a lot of time looking at people's shoes, and you guys are all well dressed for lab. Cover your sleeves. You might want to wear a lab coat to make sure your sleeves are covered, but yes, you're going to want to tie back that long hair. We may be working with open flames. So I do have a funny story that I like to tell my students about working with open flames because when I was in high school, there was a girl who was trying to impress the guy next to her, and there was an open flame, and she did that hair flip, and it goes right up the back of her long, kind of greasy hair, and it smelled absolutely horrible. She was freaking out, because people are smacking her on the back of the head, and, her hair is on fire. And you only need to see somebody set on fire once to remember that, hey, tie back your long hair. So yes, we might be working with open flames. I'm going to have to check with Dr. Hatab on that, but that might change which events we're working. And so I will find out, but there is a distinct possibility that open flames might be a thing. You're going to need those N95 or KN95 masks where the cement testing is being done. We will try to get us 2 rooms so that we don't have to have everybody wearing the masks the whole time. Participants removing safety clothing, goggles, or handling materials unsafely will be penalized or disqualified. Supervisors will provide reagents, additional glassware, or references needed. So if you need a periodic table or standard reduction potential or what have you, we will try to make it as amenable to the process as amenable to the students as we can. So what are they going to do? First thing they need to do, and the most important thing, is they're going to build a concrete puck 4 centimeters in diameter with a tolerance of plus or minus 0.2 centimeters out of whatever combination of Portland type 1 or 2 cement, sand, gravel, and water that they wish. The pucks must be at least 10%. As far as I can figure out, those are the only materials that are allowed to be in that hockey puck. Because if it was me, the first thing I would do is I would try to reinforce it with some dental floss and make myself a nice dental floss support in there, but I do not think you could do that. The pucks have to be totally dry. When any of the inside is found to be moist, if the puck breaks or crack, that puck is going to be disqualified. So they got to dry it out. They're not going to be deliberately cracked open, right? So it's only if for some reason they drop. It may be up to, we're going to have up to 1 centimeter thick. All right, 1 centimeter thick for state and a half centimeter thick for national. So as they go up in levels, that thing gets thinner and thinner, and it's going to get breakier and breakier. I have a URL on there, Engineered Concrete Interactive Science Lesson number 7. I'm not going to play the videos unless we've got time to do them because I want to make sure that I answer all of your questions first. But this will be recorded and you guys can get a copy of this PowerPoint so you can look that up. All right. So design log is a big part of the points. Every team is going to have a design log, and that design log is going to have the following 4 sections. A front cover with the school's name, team number for that competition, and the competitors' names. Again, this is something I need to tell my students on a regular basis is step 1, put your name on the lab notebook. I did that 2 semesters ago, and I made a big point about it. And sure enough, at the end of lab number 1, I'm like, here's a lab notebook. Surely I can figure out whose it is because they put their name on it. They did not. So now I hand out Sharpie markers when we do that part. Yes.
So this is my first time that I talked to someone else about report, and he said that sometimes you have to like change a team up last minute because of double booking.
Fair enough.
So like, they get there to write their name on it, or does it have to be already done?
I would write their name on it before and add as people join the team. So if somebody drops out the day of, right, line through it, and then I would keep everybody's name that might possibly be in it on it, and then cross it out the day of. That's what I would do. Good question. Front cover of the name, team number for that competition, competitors' names, a list of the components, including quantities or ratios of each. So that must be one of the categories that they are tracking is what is your material composition used in the construction of the puck. A data table for at least 10 trials. So they've got to make at least 10 of these things of different amounts of material used for the pucks and how they perform. So that means they're probably going to make 11, 12, maybe 13. Do not worry, because if you buy the quick read bag, it is like this big and you will have plenty of material to work with. A graph of the data from part 3. So any type of graph would be good. Bar graph is fine. Just some sort of graphical analysis of the data so that they're not just saying, here is my stuff and it's in a table, and then they run away laughing going, I'm done. I'm gonna go play some Minecraft. Right, so something. I've got kids. So the competition part, when they're actually going to test it, we're going to be dropping these guys at heights of 20 centimeters to start and going up in 20 centimeter intervals until it cracks or they reach 100 centimeters. Right? Tournaments will specify ahead of time what the pucks will be dropped on, and as of right now, it is the lab floor. So it's going to be that standard hard lab floor tile stuff. I do not have a large steel plate in my possession, otherwise I would do that. The puck testing may be done in the same room as the testing lab activities, in which case everybody has to wear their N95 mask. I will try to get us 2 rooms so we do not have to do that, because I know that these things are uncomfortable. Basically, if you're doing the lab portion, you got to wear your regular PPE. If you're doing the puck testing, it's all the things. If you're doing the test, it's none of them. I do not think I'm going to be able to get 3 rooms. I will do my best to make people as comfortable as possible. Masks and goggles only need to be worn in the area that we're testing the lab stuff, and the mask only in the area where we're doing the drop. All right. So pucks are going to be dropped by the students. And this is not how I would design an experiment. I would have one person consistently doing the drops, and I would have a machine doing it, but they're going to drop them. It is to their advantage to drop them as flat as possible and not throw them on the floor, but You never know. The puck should have 90-degree sides to the flat surfaces. All right, so that was buried somewhere in that. So straight up and down, cross, good. Slopey, no. Because if you look at that video from step 7 or one of the resources I'm going to show you, they're basically mixing up their concrete in like little styrofoam bowls and using them, which is going to give it angular sides. So that would be a no. It's got to be orthogonal sides, right angles. They have 1 minute to get ready for each drop. Teams may clean the surface of the puck before it is being dropped during their event time, but it must remain dry. So they can't polish it up. Right? So they can dust it off, but they can't wash it off. All right. So that's the drop testing part. You guys have any questions about the lab notebook or how we're going to test these things? I think that part is pretty darn straightforward. Okay, the test. Now, the test is not necessarily just going to be focused on concrete. There will be some concrete questions on there, 100% sure of that. But we've got a pretty big subject area to cover. The topics are going to be split into these 6 categories, and I will do my best to design the test so that it is going to follow those 6 categories in that order, because organization is important, especially for little people. So we're going to talk about material design, material structure and properties. So how does the structure of something change its physical properties? So for example, diamond and graphite are both allotropes of carbon. They are the same material, but they have different structure and then therefore radically different properties. Go try and get your fiance a graphite ring, and you will find out that those have radically different properties. Defects and imperfections. So oftentimes we're looking at things in material science like, why did this bridge fall apart? So things like material defects and imperfections will be important. Characterization techniques are, how do we know the structure of things? How are we going to classify our material? Mechanical properties. So those are things like stress, strain, breaking point, elastic modulus, all those physicsy things. Thermal and electrical properties. Is it a good conductor of electrons or of heat? Is it a semiconductor? And then 6 is applications. What do you do with those things? If you look at the URL here, so that is Wikipedia. That is going to give you lots of information about those 6 categories. So this is a really good jumping off place. That is probably the jumping off place I will use to make the test and be like, oh, these are definitely some things they should have seen and should know. I will probably find some things that are going to be a little bit harder, that are not necessarily going to be pulled straight out of there, things that might make them think a little bit, because the test part, I think, is really what's going to separate one team from another team. The lab part that we'll get to in a bit, unless things go radically wrong, they should probably going to have roughly on parity lab skills, I would think. And then unless people do weird stuff with making their concrete pucks, that's probably not going to be a big source of difference. So it's going to be the written part. How well did you keep track of stuff in your notebook? Do you have all 10 testing things? Do you pass the test as best you can? All right, so that's probably, my guess is that's where we're going to see the real differentiation is on the test, but we'll see. I've never run this particular event before. Last time I did detectors, and before that I did music. So we're in different territory for me. The written test will focus on the chemical structure, crystalline structure, characterization, performance, processing, and applications of ceramic materials. So that is going to be the focus. That is not going to limit things. So it's going to be kind of focused in one area. Doesn't mean there won't be stuff in other areas. The structure, we're going to cover crystalline structure in the test, amorphous classes, interatomic bonding, cation, anion, radii, state and national levels. We could include grain boundaries, imperfections, atomic point defects, vacancies, interstitial cations, impurities, Frankel defects, and Schottky defects. And if you want, we can go into some of those, but you could also just direct your students to figure out what all of those things are so that you don't have to know them. It's important that they know them. Processing, how are you going to make a ceramic glass? What are fabrication methods? We talked about phase diagrams, time, temperature, what the other T, diagrams, porosity. So what kind of mass to volume ratio do they have? Different characterization techniques, so X-ray diffraction, optical, electron microscopies. There are lots of different materials characterization techniques out there. Questions so far? Yes.
So again, at first you said there are going to be 3 parts.
Mhm.
It was like forgot and build something else.
So there's a so there's 3 parts. Yes, there's going to be I'm going to build my hockey puck, make a notebook for it, and then we're going to drop it. All right. And then there is the written test, which is the part we're on now. So straight up written test. And then part 3 is going to be a lab activity or activities. And that is the vaguest part. So I am still getting as much clarification as I can for like what is legit in there. But yeah, they're going to need to come in, put their lab coats on, and then do something in the lab.
Second question. So like if I have my students, like, and I do have like a couple that are interested in concrete. So if they're doing like a lab notebook to build and test, you know, we format that. Is that notebook going to have to be impounded or anything? Are they going to have access to it?
I do not know. It did not say that I'm going to collect those notebooks and give them back or not give them back. My suggestion is, and it would tremendously help me out, is if they could just like make a photocopy, like have the physical copy, and then here is a photocopy, and then they can leave the photocopy with me, and then they can take their original back with them. That just would help me out, and then that avoids the do I need to impound it or what have you. So that way I can have something, and then I don't have to like real quick go through and check all their stuff or have the TAs do that.
So
Mhm.
they can bring in 1 sheet of paper
Per person.
per person. But they couldn't have their notebook in that, could they? Like the notebook would not be allowed for the written.
No.
That's the way I'm gonna have them do their research. It's gonna be all in that lab notebook.
Okay, I see what you're.
That's
So
fine.
I would, yeah. In that case, I would say that they're not going to have access to that notebook. Transfer the stuff to their laminated 2-sided sheet per person. Other questions? All right, carrying on. Yeah, so you can, how do you characterize those things? Could be part D, mechanical properties, so density, hardness, elastic modulus, flexural strength, compressive strength, fracture toughness, brittleness, fracture, calculation of stress strain. We could include calculation of elastic modulus, calculation of flexural strength. So when they say focused on ceramics, like the whole idea of testing something like Young's modulus, we would do something specifically on a ceramic material rather than a metal. So try to make the specific examples ceramic-y. Why ceramic-y? Thermal and electrical properties, heat capacity, thermal expansion, thermal conductivity, thermal shock. Also insulation, electrical properties such as conductivity, piezoelectricity, or dielectric properties. And then F would be applications of ceramics or glasses. So what are we going to use ceramics and glasses for? So you can see better. All right. All right. Competition part 5 is the lab activity. At least one lab activity must be performed in addition to the puck testing and written test. Topics for the lab activity shall be consistent with the topics listed under part 2 written test. So since it's material science, that's a really broad category. Right? So if I go to the URL there, they do have this list of core competencies for the chemistry stuff as part 1 of this document. Pretty straightforward there. There is the URL for what you're expected to know for chemistry. So it's basic stuff like you know how to wear your PPE correctly and your goggles go on your eyeballs, right? And not on your forehead, right? And you only need to see somebody in a small lab explosion have their face covered with shards of glass and full of blood, and you're like, maybe I should wear my goggles. So things are a lot safer now than they used to be. So are you wearing your PPE? You should know how to light a match, a candle, and a Bunsen burner. Uh, my first job as a TA, sitting there and we're doing an experiment. We had to light our Bunsen burners, and everybody's got their Bunsen burners, including the two ding dongs in the back right of the room, who you're like, I'm making sure that they're not getting too much Bunsen burner. And in the front, there were two ladies who were like, Bunsen burner's not lit. And I'm like, what's wrong? And they said, oh, we always had a boy do it for me. And I was so mad. I'm like, oh no, you guys are going to light and relight that Bunsen burner 5 times while I'm watching a boy do it for me. So make sure that they know how to light a Bunsen burner by themselves.
Striker.
With striker, yes, we will have strikers. How to do both a strip and sheet of paper chromatography and do RF values, not relevant to what we're doing. How to use standard chemistry measuring instruments such as graduated cylinders, thermometers, probably won't do pH paper, conductivity meters, multimeters, calipers, and rulers. All right, one of my lab partners in high school who went on to MIT did not know how to read a thermometer. So we want to, he's a brilliant guy, but like, what are you doing? Let's not write at all. You know how to use basic glassware. So quantitative transfer, reading a meniscus on that graduated cylinder. We're probably not going to titrate filter. We might mix something, cleaning, weighing by difference, things like that. All right. Questions about the basic chemistry stuff they should know. All basic lab stuff.
Can I go back and ask?
Yes.
Fixated on the
Okay.
But did anyone have a good suggestion for a mold or whatever for 4 centimeters?
I do not. I would get a piece of cardboard, cut it to the right diameter, fold it, and then make it that way. I was thinking like, well, what can I get that's exactly 4 centimeters that's going to have straight side? There may be concrete molds at like Home Depot and stuff for making posts. Now, I don't know if that's in 4 centimeters though. I know the largest size they have is 24 inches because I want to make a telescope at one point in my life that was really big, but cans of Coke might be, I don't, yeah, 4 centimeters plus or minus 0.2. So I don't know if that's, I did not bring a physical example of 4 centimeters. So the idea that it might be hard to get it out of the PVC pipe, so maybe just line the inside of that with Vaseline before you do it. Otherwise, you'd have to cut it out. Now, there is also nothing saying in that rule that you cannot get something bigger and grind it down, but
I all around it.
and then compress it. Well, you can do that too. It's not a bad idea.
So we go find if they exist, PVC pipes, you cut them to that and maybe somehow attach it. Yeah, it'd be like on the bottom. So you cut just one slit in the side. So you put a rubber band around it. So then you pour it in, you let it set, rubber band off, collar off.
Yeah, so you make a 2-part or 1.5-part mold, and then it demolds itself. Where were we? Lab activity. So it's going to be something related to those things. Gen Chem lab skills. We did that. They have to wear PPE. So it should be looking like our example up here with our hair in a ponytail, because we might have fire. Gloves are optional. We will have them available if students want them. Lab coat, long pants, closed-toed shoes, right? Because if some glassware breaks, we do not want them finding that with their littlest piggy and going wah, 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 all the way to the hospital. It's going to be our fancy goggles. They cannot just use eye shields. Um, so if they get, and they have to wear the mask when we're doing our hockey puck drop. Participants removing their safety goggles or clothing will be penalized or DQ'd. So remind them to keep their goggles on the whole time. I know how tempting it is to want to take those suckers off. All right. Questions about their PPE that they got to wear? Great. All right. We will provide any materials needed for the contestants for the lab section. You have to provide the PPE, so category C goggles, lab coat, gloves are optional, closed-toed shoes. We might do something like any one of these things. These are the examples that they have given us: heating a small ceramic sample and measuring the melting point, recording how the melting point correlates with type of bonding. So I've got a covalent compound like sugar, and I've got ionic compound like salt. What are their relative melting points? And how does that structure relate to how does their melting point relate to their bonding type? Measuring porosity and density of ceramics. You'd measure the mass and volume of a ceramic sample before and after soaking it in water, and then you could calculate the porosity and density. Cogitating on how they could do that. So the easy way to do that, right? How are you going to do a regular? I was thinking about that this morning when I was in the shower. I'm like, how are you going to calculate that? Because ordinarily, what are you going to do a density experiment is you're going to take yourself a graduated cylinder, you're going to fill that to 5 milliliters, you're going to drop your thing in, and boom, the level goes up, and you're like, I did a science. Now I know what the volume is. But if that thing is porous, oh, it's not going to quite work that way, is it? Right? So your first instinct is wrong, but there are definite ways to solve that if you have a balance handy. Because you'll know how much water got absorbed, and then you can figure out what that extra volume of water needs to be. So calculating porosity and density, electrical conductivity, so you connect a ceramic sample to a multimeter and measure electrical resistance at room temperature before and after heating. In the process of doing all of the research for this, I did stumble upon some cool stuff with piezoelectrics that I might work into one of my PChem labs. So maybe I'll give them some piezoelectric and non-piezoelectric crystals and have them test which one is which. Right? Give them a multimeter or a oscilloscope or something, but I don't know. Right? So here are some of the, given the radius of a cation or anion, determine the type of crystal structure. So this is stuff that they put in this lab activity. I think this more relates to like the test. This is more testing stuff like, okay, here's some cation radii and anion radii. Tell me what this is. It's not very labby to me, but this would be perfectly good test questions. I did put some URLs on here for different figuring out the radius of a cation, where I got all these pictures from. Some of them are from the rules here are coming from that bottom right URL. So that's some of our default files. But so should they be able to look at a basic unit crystal structure and tell me if it's body-centered or simple cubic or face-centered cubic, and then given the radius of the atoms, determine which one of those it is more likely to be, and then what the volume would be, or go backwards and tell me what an ionic radius is. Here's my crystal lattice. It's got this density. It's got how many atoms per center. How big is the radius of a platinum ion or something? So we could go back and work those equations 2 ways. But I think that's a little bit more testy than it is labby, but that's where they told me to put it. Okay. Give examples of how structure and performance are related. So is your microstructure going to determine how something behaves? And the answer is usually yes. Know the differences between sintering and firing. So there's a URL on there that tells you the difference between sintering and firing something, which we actually do in my inorganic lab. So we made a phosphor the other day and then use that to make some glow-in-the-dark dinosaurs. So determine the structure and crystal from a diffraction pattern. So there's 2 different diffraction patterns. One is going to be a 2D diffraction pattern, and the other is going to be a angular-based diffraction pattern. So identify which of those is simple cubic and which one of those is face-centered cubic. I do not think I would ask them to actually run the math on that, just because that would be kind of hard to do. That is some. I do not like doing. I am not a math. I am not a let's sit down and do some math as a test kind of person. Math is fun when you've got plenty of time to do it, not when you're being forced to do it fast. Fast math is bad math. But recognizing which pattern is which pattern goes with which crystal structure is, I think that would be askable. These are some of the examples I found. Given a Bunsen burner, borax, and a group of pieces of metal wire produce a glass bead of a certain color. And so if you go down to this, this is where I got these A, B, C's, and D's. That's from the official website. But then this right here, this teacher manual for classroom kit, all lessons.cgif.pdf. That's a lot of these activities. So my suspicion is that's where they got a lot of these ideas from. So number one is given a Bunsen burner, borax, and a group of pieces of metal wire, produce a glass bead of a certain color. And there's a little YouTube video for that, so we can watch that if you want. B, given a candy bar, 2 sports, and a string with 2 styrofoam cups and a pile of pennies, determine the elastic modulus of the candy. So basically, they're going to take a candy bar, put it between 2 fixed points, and just add mass to it until the candy bar breaks. And you can figure out what your elastic modulus is. Use a piezoelectric device to light up an LED. So they got a little piezoelectric, and then they tappity, 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 and the LED goes blinkety, 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 because that's what piezoelectrics do. As you deform the crystal lattice, it's going to create a electrical potential, and then that electrical potential can be used to drive the LED. D is given a pan of Hot Jolly Ranchers and a popsicle stick, draw out a glass rod 12 centimeters long. And there's a YouTube video for that guy as well. And we can watch that. The bottom one, that's a little bit smaller. They made a bubble rather than a rod. Okay. Scoring. All right. High score is going to win. And it's going to be your design log, plus your puck testing, plus your written test, plus your lab activities. The design log is 2 points per section for 8 points max. Your puck testing is 2 points per survive drop for 10 points max. Your written test is going to be your written test score divided by the highest test score. So that will be normed to whoever does the best. And so it will be curved so that you can tell them not to freak out or cry. There's no crying in baseball or in the chemistry lab. You go to biology lab and cry. So that's going to be 50 points on there. The lab activities is going to be 32 points. So it's lab activity score divided by the highest lab activity score, and ties will be broken by pre-selected questions on that written test. This is what the team checklist is going to look like. So we will have a copy of this for each group that comes by, and we'll hold that in our hot little hands, and we'll write down all of the things as we come to it. So we'll look at the design log, and it's got a front cover. Our design log has the components and the ratio of each used in the construction of the puck. It's got the data table with the 10 different views, and it's got a graph. So we'll go through in true and false all of those things. We're going to circle the distance at which it falls apart, and we're going to give them the written test score and the raw lab activity score. So those will end up getting normed to whatever the highest score is for part 6 and part 7. And then there's a field for, do they get DQ'd? And I've never had to DQ somebody before, so I hope I don't have to now. Okay. Questions about what's going on this thing? All right. I think the only reason somebody would get a DQ is they really had a flagrant safety violation, or they didn't let their hockey puck dry out. So let's make sure that those things are good and dry. So there are some official questions that have shown up. Oh, I didn't highlight that. So these are the official questions. We'll talk through those one at a time. Does the radius have to be consistent throughout the puck? It can start with a radius and then converge into a dome with a smaller radius. And the answer is it has to be consistent. Plus or minus 0.2 centimeters the whole way through. The thickness was I forgot what our thickness was for this one. 2 centimeters for this one. So it's got to be the right diameter all the way across, same thickness. Can't be all wavy gravy. It's got to be round. Or a good approximation for round. Is Quikrete an acceptable base to which sand, gravel, and water can be added? It consists of Portland type 1-2 cement, sand, gravel, which are all allowed ingredients. And it says pre-mixed concretes with sand and gravel already added to them are not allowed because you can't determine the percentage of concrete, sand, and gravel in the mix due to batch variability. And I think that whoever answered this kind of misread the question, because you can buy Quikrete brand Portland type 1 cement out there at Home Depot. It's just that if it's pre-mixed with the sand and the gravel, that's a no-no. So if you just buy the cement, you're good. If you're buying it pre-mixed with sand and chunky bits in it, no, right? So no chunks, right? Oh, rules. Fantastic. So must the pucks be homogeneous? Are teams allowed to have a different composition and different types of the puck? And the answer is you can have different compositions throughout the puck as long as it is 10% cement and sand and gravel make up to the rest of it. I was thinking about different ways you could possibly cheat on this, or what I would do as a clever student, like, can I get a chunk of marble and then do a nice little, make an Oreo? So don't think so, as long as it's 10% and it has to be gravel, but it can be it does not have to be homogeneous. I mean, which would be really hard because it's an aggregate material, so making it homogeneous would be next to impossible anyway. But I think it's really like, can I make an Oreo? And then I think the rules say yes. What are the restrictions on the edge radius? So does it have to be perfectly cylindrical? And the answer is yes, the edge radius must be within that diameter. So plus or minus 0.2 centimeters. So I will be buying myself some calipering these guys to make sure they fit within the rules. Okay. What is the minimum size of a chip or a crack? And it's any visible change to the outside will be considered a failure. So if it chips, cracks, I mean, if you dust it off and you can't see it, then good. But otherwise, if it's visible to the human eye, it did not pass that test. Yeah. I mean, I was thinking like, what would I do? Like, okay, I would try to maybe take my concrete and then have like a very thin layer of plastic on the outside or rubberized material, but you can't because it's got to be sand, gravel, and concrete. So those are your only 3 allowable materials. All right. So that's the end. If you want to, you guys can make like a hockey player and get the puck out of here, or you can sit and ask me some more questions, or we can watch those videos in our remaining 10 minutes. What you guys want to do? I'm at your disposal. Yes.
So, be clear, this is for up to 2.
Mhm.
One student could enter it and just do it by themselves, right?
Yes.
Okay. So, and we can have multiple teams per, like if I have 2 students, if I have 10 students.
Could you do multiple teams?
Right.
I do not know. I would check with Trixie or somebody else higher up than me.
As many people as want, but I'm pretty sure with regional, we had team A and B, but then when we went to state, we only have 1 team. So I'm pretty sure. Yeah, so I'm pretty sure regional, we still have A and B, but not C.
But put on teams, not just like 2 big. You have like an A team with like you have the B team.
But they're saying that within that 18, you could have like 2 different ones.
No.
Yeah.
Within that, that's good. You have like 1 set of students do 1 thing, 1.
So you'd have a group of 15, and then only 2 of those 15 would be in this event. That is what I think it is, but okay. That's, yeah, I've never had 2 teams from one group of.
large.
Yeah.
They have like teams, they do that 3 entry. But like if I'm a small team, I can only have one entry. It's I have one team. And this material science hockey puck, they bring one puck. I mean, can they bring like a backup puck?
Yes, you can bring it back, but you can only test the one. So I mean, you can't be like swapping out in the middle. You can't tag team that, right? It's got to be whichever the best one is that day. You're going with that one. But yeah, I would have them bring a backup just in case it gets damaged in transit and it gets bumped around in the back of the car, or somebody's like, whoops, and they throw their backpack with a hockey puck and you hear a crack and you're like, oh. So even if it does break, though, still have them compete, because if they're really good at that written test, which is about 50% of it, or the lab stuff, that hockey puck is not the whole shebang, right? So they're going to start off on round one and bottom that out. But if the other teams didn't study and do their homework, they could still take that home. So
Do you know about how long for this whole competition lasts?
about an hour.
Oh, it's only about an hour?
Yeah.
Even with the lab?
How many minutes? 50 minutes. So that's with the lab section and the dropping as well. So it's going to be absolute chaos in there, where they might be shuttling back and forth between two rooms. Somebody's I'll pull somebody apart and just be like, not apart, but I'll pull somebody away and be like, okay, you're going to do your testing now. Stop what you're doing on your test. Come on over here if you want to tag your partner out, and they're going to pick up the test tool. So it's going to be entertaining, and at least in that part. Yeah. I only got 50 minutes, and depending on how many teams there are, it might be I'm doing multiple, everybody does their drop testing. Well, I don't know yet. It depends on how many people there are and what space I've got. So it might be everybody's going to do their drop testing all at once, and here's a bunch of rulers and go.
But when we're talking about the lab question, I mean, it's gonna have to be a quick lab.
Yes. So I can't do anything that's going to be more than maybe 30 minutes, to be fair. There might be 2 activities. I don't know. I've not figured out what other people are doing yet. And some of those things look like they're pretty easy to get done in 5-10 minutes, like the make an LED light up. Other things like making that glass might take 10-15 minutes. So I don't know. I will try to make the lab be about 30 minutes. I will try to have I'm going to try to get 2 15 minutes in, so that if people, that way I can tell these people are real good and they got 2 things done. And then this group got 1 and part of something else done. And this group only did 1 thing. So I have to see. But I think both people can be in the lab at the same time. Both people can be working on the test at the same time. I would try to think about how you're going to assign those people different tasks when the day comes. They can take their exam packet and take it apart as long as it comes back together again at the end. They will have a score sheet that they're going to write their stuff on, so they can multitask on that if they want to. Just if it is multiple choice, do not do what I did for my GRE and then miss a section and then have to go back and erase and rewrite everything. So make sure they're organized with how that was. I was so mad at myself for that, but all right. Other questions? So yeah, the lab part is the big mystery part for all of this, but if you go to those URLs, that'll tell you at least what they're doing for those example ones that they picked. I don't know what they've done for regionals at all. And I'm trying to get in touch with some of my other colleagues who are running this event to see what they're doing, so that, I'm not picking something super hard or super easy. So, all right, all the questions you guys got? Be glad to answer them. I'm looking on the Zoom. Maybe there's a question on Zoom, but I don't think so. In theory, 5 minutes, I think. Okay, yeah. Which one do you want to watch? We have Jolly Ranchers. We have piezoelectric LED. We have Bunsen burner and glass or chocolate bar. Or do you want to watch where to go? The concrete brick one. Making a concrete brick. Find that one there. What are you feeling? All right. Want piezoelectric? All right. Escape. And we'll do piezoelectric because they're only about 5 minutes. All of those are LED. Piezoelectric to light up an LED. All right. Well, we won't have any audio for that. I'm sorry. On the closed captioning for us.
Yeah.
All right, so the object is to piezoelectric effect in several materials and explain why this property exists in certain materials. The piezoelectric effect of the ceramic disc and the polymer film will be demonstrated through the use of LEDs. And they're getting this from the Ceramic and Glass Industry Foundation Handbook. And the URL for that is on the start of those pages where we talk about the lab stuff. So again, sorry, there's no sound, but it's nothing other than the guy talking over this. So he's grabbing a couple of different piezos, some polymers, some cables, a voltmeter, and a musical greeting card. Got a little piezo electric polymer film and hooking that up to alligator clips. And that's the little speaker that he took out of the birthday card there. Hooking that guy up to an LED. And tapping that until the LED lights up. Mhm.
Exactly is it generating? Like, I don't know.
It's generating a potential difference because in the crystal structure, and there is a really good video by Mr. Mold, Mould, who talks about how that crystal structure deforms. And as you apply pressure, if you have something that's got polar bonds in the crystal structure. So they're going to have a partially positive end and a partially negative end on your polar bonds. And as you deform that crystal, you're pushing them along one axis, you're changing the separation between elements, and now you're stretching out or compressing your polar bonds. That creates that potential difference. I've got that URL. If I can look for, yeah, they're just tapping that to give you different, let me find, there's my schedule. And then that video that does a really good job talking about piezoelectrics was here. No, PChem, maybe PChem. Go all the way down to 200. Stephen Mole, the British guy. So, yeah. So you guys need to go, but no, not this one. So Steve Mould, it has a good explanation. Mould has a very nice explanation on how piezoelectrics work, which again, I might be throwing to my inorganic chemistry students or my PChem students. So
Thank you so much.
you are welcome. And if you got other questions, please feel free to reach out. I will do my best to answer them or find answers if I do not know them. All right. Yeah, I will. Yes, it's all there. It's just like, it's like it was for the detectors, where it's like, we haven't done it for like 3 years. Like, what's happening?